In the last lecture of material technology, we have seen effect of strain hardening. So today we are going to see different types of significance of imperfections, as you know, and what we are going to see today actually is line defects. How line defects occurs. The line defects takes place due to dislocation of atoms along with a line in some direction. Now there are two different types of line defects that are as follows. First is a edge dislocation, second screw dislocation. Now as the name indicates, edge dislocation. In edge dislocation, a half plane of the atom is included between the planes of atoms in a perfect crystal. Then as I have shown or as I have discussed that the half plane of atom, it is going to be included between the planes of atom. Now it can be noted that top and bottom of the crystal and below the line it appears to be somewhat perfect. Let us suppose the extra half plane is inserted from the top, then defect will be produced, that is represented by inverted T. So the extra half plane is inserted from bottom, the defect produced will be represented like a regular T. So edge dislocation, as the name indicates, the total edge of the packing of atoms is going to be hampered. Whereas screw dislocation, the atoms are displaced in two separate planes perpendicular to each other, and the defect produced is called as screw dislocation. The arrangement of atoms appears like a screw or helical surface. Therefore, in exam, every time the question is asked, that is, what is the difference between edge dislocation and screw dislocation? Now, edge dislocation, we will start with edge dislocation on the left side and screw dislocation on the right side. Therefore, edge dislocation arises due to introduction or elimination of an extra row of atoms. Screw dislocation provides for each crystal growth because additional atoms and unit cells can be added to step of the screw. In edge dislocation, tensile, compressive and shear stress fields may be present. In screw dislocation, tensile, compressive stress fields are absent, only shear stresses are present. In the edge dislocation, a region of lattice disturbance extends along an edge inside a crystal, whereas in screw, region of lattice disturbance in two separate planes. Berger's vector always perpendicular to dislocation line in edge, whereas Berger's vector is always parallel to dislocation line in screw. Edge dislocation is occurring due to glide and climb motion. Screw dislocation is occurring due to glide motion. Edge dislocation is of two types, positive and negative. Screw dislocation does not show any type. Now dislocation, jog and kink. Now there was a question that write a short note on dislocation of jog and kink. The dislocation jump from one plane to another is called as a jog, and the jog in a dislocation may be regarded as a short length of dislocation not lying in the same plane as the main dislocation. Now both are typically referred to as jogs, which can be a source of confusion. Segment of dislocation line that have a component of their sense vector normal to the glide plane are termed as jogs. The sense vector and the glide plane segment of dislocation line that do not leave the original glide plane are termed as kinks. Jogs are compared to kinks and require diffusion of crystallographic defects like vacancies or interstitial atoms to climb. They are not capable of glide because the direction of motion is in the plane normal direction, not on the plane itself as with kinks. Berge vector. The Berger's vector is the magnitude and direction of shear that a dislocation produces. It is defined by means of a circuit around a dislocation on any surface which intersects the dislocation. Berger's circuit in direction of rotation of a right hand screw advancing along dislocation directions. Berger's vector closes gap in Berger's circuit. Berger's circuit would close in a perfect crystal. Now we are going to discuss motion of dislocations and their significances. First, dislocations are most significant in metals and alloys since they provide a mechanism for plastic deformation, which is the cumulative effect of slip of numerous dislocations. Plastic deformation refers to irreversible deformation or change in shape that occurs when the force or stress that causes it is removed. This is because the applied stress causes dislocation motion that in turn causes permanent deformation. When we use the term plastic deformation, the implication is that it is caused by dislocation motion. There are, however, other mechanisms that cause permanent deformation. The plastic deformation is to be distinguished from elastic deformation, which is a temporary change in shape that occurs while a force or stress remains applied to a material. In elastic deformation, the shape change is a result of stretching or interatomic bonds. However, no dislocation motion occurs. Slip can occur in some ceramics and polymers. However, other factors like porosity in ceramics, change in polymers dominate the near room temperature mechanical behavior of polymers and ceramics. Secondly, slip provides ductility in metals. If no dislocations were present, an iron bar would be brittle and the metal could not be shaped by metalworking processes such as forging into useful shapes. Third, we control the mechanical properties of a metal or alloy by interfering with the movement of dislocations. An obstacle introduced into the crystal prevents a dislocation from slipping unless we apply higher forces. Thus, the presence of dislocations helps strengthening metallic materials. Surface defects. When we talk about the surface defect, the question is discuss the surface defects. Surface defect is the defect that takes place on the surface of a material. The following are the types of surface defects, that is grain boundary, twin boundary and stacking fault. Grain boundary, that is the grains of different orations of atoms which exhibit a boundary. The defect cause is called as a grain boundary because when a liquid metal gets solidified, the defect takes place in the form of grains. Twin boundary, when the boundaries in which arrangement of atoms on one side of the boundary is a mirror image of the arrangement of atoms of another side, the defect is called as a twin boundary. In twin boundary, the defect obtained is between the twinning planes. Stacking fault, when the stacking of atoms is not in a proper sequence throughout the crystal, the fault cause is called as a stacking fault. The region in which stacking fault is obtained forms a thin region of hexagonal plaque, that is FCC crystals. Now, generation of dislocation. When dislocations move, we first have some dislocation before plastic deformation can happen. Dislocations can just be generated at the surface of the crystal. The simple pictures showing plastic deformation by an edge dislocation mechanism gives an idea how this can happen. The most important mechanism that is ideal is Frank-Reed mechanism. Now, when we talk about Frank-Reed mechanism, we must understand Frank-Reed source and conditions of multiplication and significance. The question arises is write a short note on Frank-Reed source. The Frank-Reed source is a mechanism based on dislocation multiplication in a slip plane under shear stress. Consider a straight dislocation in a crystal slip plane with its two ends, that is A and B. Now we have seen and I have provided you the technical PPT. You should go with that and you will understand it easily. We move forward. Deformation. Now what is deformation? Deformation is defined as a change in the shape of body caused by application of a force. There are two types of deformations as elastic deformation. It is the process of deformation which appears and disappears simultaneously with application and removal of stresses. A stress of low magnitude is applied to a piece of metal. It causes displacement of atoms from their original position. The removal of stress, the atoms spring back and occupy their original positions. In plastic deformation, it is defined as the process of permanent deformation which appears in a metal even after the removal of the stress. The metals may be subjected to different operations such as spinning, drawing, rolling, forging, etc. The plastic deformation occurs under the tensile compression or torsional stresses. It is a function of stress, temperature and rate of straining. There are two types of plastic deformation such as slip or twinning. The slip is common in many crystals at an elevated temperatures. Now, slip and twinning, how it going to happen? Let's understand. Deformation by slip. In this process, a large displacement takes place in one part of the crystal as compared to one that takes place in other part of the crystal. The place and direction in which it is obtained are called as slip plane and slip directions. The slip may take place in more than one plane or direction depending upon the structure of the crystals. It is a function of temperature and composition. A crystal undergoes plastic deformation whereas the arrangement of atoms in the crystal remains same. There is a small change in the density. Thus, there is no change in the volume. It is a non-reversible process. Atomic blocks will not return to the original shape after withdrawal of the forces. The shear producing slip is called critical resolved shear stress. Theoretical value of shear strength is about 1/6 of modulus, that is G by 6. In actual practice, shear stress required to produce a slip is so smaller. Energy required for the deformation can be given by E is proportional to LGB square, where L is length of dislocation line, G is shear modulus, and small b is Burgers cover. In deformation by twinning, sliding of one plane of atoms over the other is called as twinning. The total moment at any point is proportional to distance from the twinning plane. Twinning occurs from slip in the sense of that of an twinning each plane of atoms moving a definite distance. Twinning is obtained in body-centered cubic, that is BCC, and hexagonal closed pack HCP structure. There are two types of twinning that occurs. Twinning produced due to applied stress under shock loading called as strain twins or mechanical twins. Twinning produced as a result of annealing process called as annealing twins. Now we'll go forward. Significances of elastic and plastic deformation in design and shaping. In elastic and plastic deformation is the remaining when the stress and hence the elastic strain is reduced to 0. Elastic deformation is that produced in this purely plastically deformed material by the action of stresses up to yield. The total of deformation is sum of elastic and plastic rate to be in error. An incremental plastic theory is developed using the non-linear kinematics. Now we have to see the equation. An equation is called as Mills law, and the term cos alpha into cos beta is called as Schmidt's factor, and the equation given is tau CR is equal to sigma into cos alpha cos beta, whereas if alpha is 90 degree and cos alpha is equal to 90 degree, then tau CR is 0, and if beta is 90 degree, then cos 90 is 0, therefore tau CR is 0. Therefore, we can say that for all combinations of alpha and beta, the critical resolved shear stress will always be less than sigma by 2, that is the half of the tensile stress. When we consider deformation of single crystal by slip, then we have to go through equation. That equation is again tau is equal to sigma cos alpha cos beta, where sigma is the applied tensile stress, that is P by A. And as you know, P is equal to load applied along with the axis of the single crystal, and A is equal to cross-sectional area of the crystal. Then plastic deformation in polycrystalline materials, it is the question that may be asked in exam. The deformation of polycrystalline material is different than that of a single crystalline material. The reason is deformation of polycrystalline material takes place due to movement of dislocations along the slip system, which is most favorable orientation. Greater the number of grain boundaries in a polycrystalline material, higher will be the resistance offered to the dislocation moment. So, greater will be the stress required to produce plastic deformation. The fine grain material possesses high tensile strength and better mechanical property as compared to coarse grain material. So, dear friends, up to today we have seen this much. In the next lecture we will see crystal structure, that is deformability of lattice systems, then some parts related to strain hardening. Till then, thank you.